Dave did his PhD at Columbia before moving to Princeton University, and then he moved across the road to the IAS. And today he's going to talk about exoplanets and astrobiology.
Hey, well, it's a pleasure to be here. I've never been to Toronto before. Got here yesterday afternoon. I've had a good time so far. So, if I can mention briefly, a number of collaborators who worked on parts of the things that I'll be talking about today, including Courtney Dressing, who's an undergrad at Princeton, Harvard, Ed Turner, Kristen Manu, Jason Nordhaus, others. An overview of the talk, which I probably will not get to everything that I had thought about saying, but an overview of what I had planned to get to is two aspects related specifically to astrobiology. One is I'd like to get to a discussion of what factors influence climatic habitability, what I mean by climatic habitability. What are the astrobiological implications of the early emergence of life on Earth? And finally, what happens to solar systems when the star moves off the main sequence? And I'll start by presenting my conclusions, in case I don't get to everything that I was planning to talk about. So the conclusions are that dynamical interactions in a planetary system can strongly influence the long-term habitability of terrestrial planets. That abiogenesis on Earth, specifically the timing of the abiogenesis event. Abiogenesis is a word that means the origin of life. Kind of funny term. I think biogenesis would work just fine. I think the abio means life coming from no life. But anyway, the timing of the abiogenesis event on Earth does not place strong constraints on the probability of abiogenesis elsewhere. This might sound obvious, but a lot of people have thought that it actually does, and it doesn't. And finally, there are a number of interesting things that happen to planetary systems when the stars leave the main sequence. Post-main sequence evolution can lead to two populations of companions to white dwarfs, and it can heat and chemically pollute planets or other low-mass companions. So astrobiology is a word that was what got me interested in astronomy in the first place. When I was a sophomore in college, I was walking down the hall of the physics building and saw a poster on the wall that was advertising the new NASA Astrobiology Institute, and it had an artist's depiction of life on planets around other stars. It seemed like the coolest thing to spend your time studying. The word itself is about half a century old. The concept, of course, is much older than that. More than 100 years ago, when Percival Lowell and others looked at Mars, they thought they saw these linear features, which they interpreted as the canals and irrigation ditches built by a dying civilization to take water from the melting polar caps to the parched midlands, everywhere that they needed water to be. Of course, Mars doesn't actually have those linear features that they thought they saw. Farther back, several centuries ago, in 1695, Christian Huygens finished writing his treatise Cosmotheoros, subtitled in translation, New Conjectures Concerning the Planetary Worlds, Their Inhabitants and Productions. And in this document, he pointed out that the moon and the other planets in the solar system are not so different from the Earth and probably have their own inhabitants, plants and animals, just like the Earth. And he pointed out that the other stars in the sky are not so different from the sun and probably have planets and moons with plants and animals. And he even pointed out that Jupiter and Saturn are far enough from the sun that water would be in its frozen state there. But of course they have inhabitants, which need water. So he said they have a different kind of water with a lower freezing point, which is sort of true if you think about methane and ammonia, but it's also just not true if you think about water. So I kind of like these two examples of sort of a cautionary tale for ways in which observers and theorists can be misled by hope. So extrasolar planets. I looked through the literature for the earliest paper I could find that claimed the detection of a planet around another star. It was back in 1855 by a guy who published under the name Captain W.S. Jacob. And he was looking at the binary star 7 Ophiuchi, and he thought he saw an anomalous astrometric wobble, which he interpreted as being due to the gravitational influence of an unseen companion. Over the intervening 150 years, a lot of observations have ruled out the mass of companion that he inferred to be there. So his observations were mistaken. The first actual detection is often credited to Wolshin and Frail, the pulsar planets, in the early 1990s, or to Mayor and Coelho in 1995. But I would argue that the first actual detection of an exoplanet was in 1988, when Bruce Campbell and collaborators found what turned out to be a radial velocity signature of a planet around Gamma Cepheids. Now, this is a somewhat active star, and so alternate explanations weren't ruled out until subsequent observations in 2003. Also pointed out in 1989, practically contemporaneous with the Campbell discovery. Dave Latham and collaborators found what could either be termed a low-mass brown dwarf or a high-mass planet around a solar-type star. Now, you're all familiar, I'm sure, with the idea of planet transits as a way of detecting and characterizing exoplanets. This is a really crappy animation I made. But what you might not be aware of is that the idea of looking for transits was suggested back in 1952 by Otto Struve and fleshed out a bit in 1959 by Sishu Huang. And actually, Otto Struve also, the title of his paper was Proposal for a Project of High Precision Stellar Radial Velocity Work. So he's actually talking about using radial velocity to find exoplanets, but he pointed out that transits would work too. A Jupiter passing in front of a sun causes about a 1% transit dip, which I'm no observer myself, but I've spoken to people who've worked with photographic plates, and 1% would be challenging, and might have been impossible, but might not have been impossible with photographic plates. So it's conceivable that way back in the 1950s or 60s, people could have actually found exoplanets. Otto Struve also pointed out that many people were very surprised when the hot Jupiter class of planets was discovered. People didn't anticipate Jupiter-mass planets in several-day orbits. So people often say, and many people were surprised, and actually in this paper by Otto Struve in 1952, he said there's no reason why there couldn't be massive planets in close orbits around stars. And turned out to be present. So after the first transiting planet was found, HD 209-458b, back in 2000, I believe, it was seen in transit, people got really excited about looking for transits. And this is a somewhat infamous figure from a conference back in 2002. This is predicting for 23 transit surveys that were going to go online in the year 2002, the yield in terms of the number of planets that we detected per month on the vertical axis. And then the horizontal axis is the aperture of the telescope that was going to be used for each of these surveys. If you look at this, this ranges from almost 1 per month to a few per month, up to tens, 40 transiting planets per month, for a total of 191 transiting planets per month that were supposed to be found in 2002. Of course, now we know of only about 200 transiting planets total, although there are more than 2,000 candidates as Kepler has found. So it was much harder to find transiting planets than people initially thought it was going to be. The noise caused by the atmosphere and astrophysical sources of confusion were much worse than people anticipated. But according to exoplanet.eu, last night, we now know of 843 exoplanets. Different catalogs will give you different numbers, but the point is it's a large number and a very quickly growing number. This is the number of planets discovered per year, going back up to the present. So you can see it's still a rapidly growing curve. Kepler has been a tremendously successful mission for finding exoplanets. I imagine most or everyone here has heard of Kepler. It's a spacecraft that has a telescope that's staring at one field on the sky for about half a decade. And looking in the constellation Cygnus, you can see here is the Kepler field of view. And to give you a feeling of how big that is, that right there is the full moon. The Kepler field of view is about 400 times the size of the full moon, monitoring about 150,000 stars for about 5 years, looking for the faint periodic dips caused by planets passing in front of their stars. The goal of the Kepler mission was to find the frequency of Earth-like planets around sun-like stars. Here's, oh, this is hard to see. Well, this is a scatter plot of the first, oh, that's much better, thank you. The first 1,300 planets or candidates released by Kepler. Horizontal axis shows orbital period in days. The vertical axis shows planet radius and Jupiter radii. And the color of the point indicates the temperature of the host star. So, well, let me just ask you guys. Staring at this, do you see what pops out to your eye? Point one. This, the radius. Yeah, good. Okay, so 0.1 Jupiter radii, that's 1 Earth radius. Looks like there are a lot of small radius planets. Another thing is that there are a lot of planets going out all the way to long periods. And this is significant because this hasn't been corrected for any selection effects. This is just all the candidates that are found. The geometric transit probability drops off with 1 over the orbital separation. And yet there are still a lot of planets being found out here, even though the probability of finding them is smaller, and you get fewer transits because the orbital period is longer, so it takes longer to build up a certain amount of a fixed level of signal noise. So the fact that a lot are being found out here means that there are really a lot of planets out here. So Andrew Howard and collaborators, I'll get to that slide in a moment. The exact Earth analog would be off here. This is a figure that I made last night with the latest Kepler release, 2,300 planets. So now the vertical axis, similar scale is now in Earth radii instead of Jupiter radii. And the dashed line here is 1 Earth radius, and the vertical dashed line is 1 year orbital period. So an exact Earth analog would be right there, across here. And so you can see there isn't much that's been found so far that way and that way. This sort of region, but we're getting close. Or I say we, I'm not part of the Kepler team, but people are getting close, and it's probably not going to be long before the Kepler team announces the discovery of a pretty close Earth analog. Andrew Howard and collaborators did a very nice analysis of the first 1,300 Kepler candidates discovered that showed a nice statistical steps, just what your eye was picking out, which is that the frequency of planets increases with decreasing planet radius and increasing orbital period. I'm actually not going to go through the details of this. That's what this shows. Yesterday, I also decided to just take a look at the history of planet observations to see, to see if we can sort of extrapolate anything about how long it'll be before we find an Earth-mass planet at 180. And so what I'm plotting here is the function of year of discovery. I'm plotting the minimum mass planet that had been found at a 1 year or more orbital period in Earth masses. And so you see it goes from, this here is about 3 Jupiter masses, 2 Jupiter masses, about Jupiter, down to this here is about 4 Earth masses. This was discovered in 2005. It was a microlensing planet. So we actually got, say we again, but people got lucky early. Since 2005, this value has not been pushed down yet. But again, I anticipate that, at least in terms of radii, we're not going to know the exact mass of a Kepler detection at 1 AU. But in terms of radii, we're probably getting very close to Kepler finding an Earth analog. So what affects habitability? So the term the habitable zone, can we put the light back up? The term the habitable zone is often taken to refer to a range of distances around a star that's good for life. Usually people mean life as we know it, liquid water-based life. Now, actually, of course, there are many things that affect the climate conditions on a planet. And it's not just the distance from the star. The kind of star matters. That's probably the biggest other influence. But also what the planet's made of, the atmospheric composition, the distribution of land and ocean. You can imagine a multi-dimensional parameter space that describes the planets and their stars. And I like to think of the real habitable zone as being some cloudy region, and it might not even be a simply connected cloudy region in this multi-dimensional parameter space. One of the dimensions is orbital separation. And so if you hold everything else fixed and you shoot a trajectory through this cloud parallel to the orbital distance axis, then it will penetrate the cloud at an inner radius and at an outer radius. In fact, you don't need to hold everything else fixed, you just need to specify a trajectory through the cloud. You get an inner radius and an outer radius. And that's what people typically call the habitable zone. But there's no a priori reason why there has to be only one trajectory through the cloud. So something that I've thought about is how might we look at the contours of this multidimensional habitable zone in a less geocentric fashion. So here was an early attempt at doing that by Jim Casting and collaborators back in 1993. This is sort of an iconic figure from a seminal paper that Jim Casting wrote, showing the classical habitable zone, where we're looking, the horizontal axis is orbital separation in AU. The vertical axis is stellar mass, which is sort of a proxy for stellar luminosity. You see what he's calling the habitable zone here goes from close orbits around a dim star to distant orbits around a bright star through the output. But this is, again, thinking just about the properties of the star. Properties of the planet, the rotation rate, the distribution of land and ocean, the composition of the atmosphere, the obliquity with the tilt of the spin axis, the orbital eccentricity, and the long-term history of the climate all can affect the climatic habitability as well. These bottom ones, which I listed in yellow, are attributes that are strongly influenced by planetary system architecture. The others can be also, but these probably somewhat more so. So if you want to put together a simple climate model, the simplest model would be just to figure out what's the temperature of a planet, where you treat the temperature of a planet as being just one number. The planet's the same temperature all over. Basically, you're treating it like a speck of dust, although maybe a speck of dust that has an atmosphere. That's basically actually what was used in the casting model. Well, he called it a 1D climate model, but the 1D is vertical. Horizontally, it's a 0D climate model. So if you want to put together a model, you want to think about the heating function of the planet. Or what I mean is, how strongly is the planet being heated as a function of its temperature? So the stellar radiation is not a function of temperature. So I'm drawing straight lines where the planet's close to the star, it's heated a lot. If it's far from the star, it's heated less. The albedo of a water-rich planet might be a strong function of temperature. Right around the freezing point of water, we go from shiny snow and ice to very non-reflective liquid water. You take the product of these two, and you get the heating curve. The heating curve is the irradiation times 1 minus the albedo. So again, far from the star, the heating curve is lower. Close to the star, the heating curve is higher. Combine the heating curve with the cooling curve to find the equilibrium temperature. So the cooling curve looks something like this. The outgoing irradiation is a function of temperature. It's an increasing function of temperature. The planet is not a black body. It's modified from being a black body by the atmosphere, specifically the greenhouse effect, or an anti-greenhouse effect, which can exist also. But this is qualitatively the basic shape of the cooling curve, at least at temperate temperatures. If you put them together, and this is a somewhat busy figure, but let's look at So here we're looking at these dotted curves are heating curves at different distances from the star. Vertical axis is flux, horizontal is temperature. The solid curve is the cooling curve from a reasonable atmosphere model. And if we look at the 1 AU heating curve, we see that it intersects a cooling curve that's kind of similar to the Earth's cooling curve in 3 places. Each place that it intersects is an equilibrium temperature. The middle one is an unstable equilibrium. You perturb the temperature a little bit from there, heating exceeds cooling, you run away to the upper one, or you run away to the lower one if you perturb in the negative direction. There are 2 stable equilibria at 1 AU. This one here corresponds to today's climate. This one down here, very cold temperatures, globally frozen, corresponds to what's often called snowball Earth. And many geologists, it's not completely universal, but many geologists think the Earth has been through at least one snowball state in the last billion years. Now, if the Earth did go through a snowball state, it presumably, well, obviously melted out. And presumably this happened by volcanic activity releasing a lot of greenhouse gas into the atmosphere, allowing it to melt down. So I put together a climate model that's one-dimensional in one horizontal dimension instead of 0 horizontal dimensions. This allows you to see time-dependent behavior, allows you to capture time-dependent behavior even in the absence of orbital eccentricity. And it's from a class of models called an energy balance model. Kind of a vague term, but it means a specific kind of thing in meteorology. It's a sort of model that was used for many years for calculating Earth climate back before computers were sophisticated, fast enough to do full 3-dimensional climate simulations. And you might wonder, now that computers are fast enough to do full 3D climate simulations, what's the value of using a simple energy balance model? The basic idea of the energy balance model is that it treats the redistribution of energy as a diffusive process. And there's a long history of literature in the Earth climate community looking at in what circumstances this is actually a good approximation. And it turns out that on large enough distance scales and over long enough time scales, it's actually quite a good approximation. Ed Lorenz had a nice paper justifying this. So why would you ever want to use a simple EVM when you could do a 3D general circulation model, a GCM? And there are a couple of reasons. One is that even though we can run GCMs, they're still not cheap to run. There's an EVM, you can run hundreds of years of simulation in just a few minutes. And so as part of my PhD work, I ran 10,000 climate models or so, which wouldn't have been possible with a general circulation model. So you can run many of them. And the other is that they're simple enough that you can understand why you're getting the answers that you get. If a model is sophisticated enough, it can be almost as hard to understand why the model is giving you a certain answer as to understand why the weather gives you a certain weather. So there's an advantage to have a model that's simple enough that you can understand, but it can be a disadvantage if, although you're understanding it, it's giving you the wrong results. So before you believe in EVM, you need to validate it and check if it actually does give reasonable answers. So this is showing you for my model set up with Earth-like conditions, the annually averaged temperature, that's the black curve, as a function of position on Earth, latitude. And the green is the Earth's actual annually average temperature. It doesn't vary much from year to year. This is from 2004. And what you can see is that at all latitudes north of about 60 degrees south, the model is within a few degrees of the Earth's temperature. Below 60 degrees south, the Earth has a very shiny, high-altitude continent that wasn't present in the model, so it doesn't match precisely there. Looking at the temporal variation, so this is spatial variation. Looking at the temporal variation, here we're looking at as a function of both position on the planet, show the different colors and the different line types, and time of year, from the northern winter solstice, so that's December 21st, that's June 21st. Looking at the temperature, and this is for the model, and this is in the Earth's oceans. And what you can see is, not only qualitatively, but even quantitatively, the model does a pretty good job, actually better than I expected, of reproducing the annual variation and the spatial variation of temperature on the Earth. Now, one thing that might look a little surprising when you look at this is that this is saying that in the northern hemisphere, the coldest day of the year is March 21st, and the hottest day of the year is September 21st. This might seem a little weird. It's like the coldest days in February and the hottest days in July. But remember, this is capturing the average temperature of the Earth. This is showing exactly what happens in the ocean. And the reason why this happens in the ocean is, if you think about a damp-driven harmonic oscillator, if the forcing frequency is much faster than the response frequency, then the response will lag the forcing by a quarter cycle. And that's exactly what you're seeing here in both the model and in the Earth. The coldest day is offset from the forcing by about a quarter of a year. And that's because the oceans have a thermal time scale of about a decade. This is the portion of the ocean that interacts strongly with the atmosphere has a thermal time scale of about a decade. Land has a thermal time scale that's less than a year, and so that's why the time lag is much less if you're living on land than if you're living in the ocean. I'm actually not going to go into the equation that I solved unless people are interested. But using this model, which I also validated by comparing to general circulation models in just a moment. So that was validation comparing to the Earth with an Earth-like setup. I also validated the model by comparing to less geocentric setups, where the planet is at high obliquity or where the planet has high eccentricity. And I didn't put the model validation slides in here, but the model produces very similar results to what a full 3D general circulation model produces. And it allows you to do a rapid parameter study. So this is looking at the distribution of exoplanets, eccentricities, and masses from a few years ago, but the basic shape of the distribution hasn't really changed. The vertical axis is a log scale planet mass and Jupiter masses. The horizontal axis is eccentricity. And what I want you to take from this is that planets of all kinds are showing up with all eccentricities. There's some extremely high eccentricities, over 0.9. 20% of the known exoplanets have eccentricities bigger than 0.4. For comparison, the crazy eccentric planet in our solar system, Pluto, has an eccentricity of only about 0.25, and it's not even a planet anymore. So our solar system might be surprisingly dynamically cold in comparison to the exoplanets. It's not necessarily clear that that's the case, but what is clear is that there are a lot of exoplanetary systems that have moderately high to very high eccentricities. Also, if you think about obliquity, there have been several planet dynamics theorists who have done calculations that suggest that we ought to expect a widespread in planetary obliquity. This is a figure from a paper by Kokubo and Ida in 2007. There have been others who found similar results. What this is showing is the solid curve is for it's a histogram of the obliquities in a simulation that they ran. So they did a planet formation simulation and then had the planetesimals interacted and formed planets. And they tracked the obliquity of the forming planets. So this is the obliquity angle, and what you see is that it's spiked. The distribution peaks at around 90 degrees obliquity. So that's the spin axis on its side, which is basically what you expect from an isotropic distribution of spin vectors. Now, this might not actually be true. It doesn't seem to be what we see in our solar system. Earth has a fairly low obliquity. Mars also has a fairly low obliquity. Although Mars' obliquity does scan a wide range, and Earth's would as well, if either we didn't have a moon, or even with the moon, if Jupiter were in a different place. So they would argue that we happen to be lucky in our solar system to be at a certain point in history when both the Earth and Mars have fairly low obliquity. They would argue that we ought to expect a wide range of obliquities, and perhaps the distribution is peaked towards 90-degree obliquity for exoplanets. Here's a nice paper by Darren Williams and David Pollard, 2003, looking at the effect of obliquity on, so here they're looking at an 85-degree obliquity Earth on the distribution of temperature on the planet. So here they took a detailed model of the Earth. They just changed the obliquity, so it's almost over on its side. And what ends up happening is in the northern hemisphere, where there's a lot more land than in the southern hemisphere, has really huge thermal extremes. So in the northern summer, the temperature gets up to about the boiling point of water. And in northern winter, it gets extremely cold. The ocean areas are much less affected. You'll often hear people say that the Earth needs a moon to keep us habitable, to keep our obliquity from going crazy. And it might be that the moon has been important in allowing complex land-based life to arise, but it's by no means obviously that we couldn't have had pretty complex fish, even with the obliquity changing quite a bit. And furthermore, people have I think, incorrectly extrapolated this to thinking about exoplanetary systems and said that in other planetary systems, terrestrial planets need to have a moon in order to have a stable obliquity. And that's just not true at all. There can be orbital configurations where having a moon actually makes the obliquity less stable than not having a moon. Working with Courtney Dressing and Sean Raymond and some other people a few years ago, we took a look at what happens if you vary both the eccentricity and the obliquity at the same time. So what we found is that for low obliquity, even having moderate eccentricity doesn't, just tell you qualitatively. For low obliquity, eccentricity doesn't have much of an influence on the location where a planet freezes over, orbital separation where it gets too cold for liquid water. And for low eccentricity, the obliquity doesn't have a strong influence on the outer boundary of the habitable zone. But there's a synergy between the two of them, where if you have high obliquity and moderate eccentricity, that can result in a big change in the outer boundary of the habitable zone. So what we're looking at here is the vertical axis is orbital separation, same major axis. The horizontal is eccentricity. There are a range of models plotted here. People have often taken the influence of eccentricity to just scale with the annually average stellar radiation.
What do you mean by snowball transition?
When the planet freezes over, globally freezes over.
So there's the three equilibria. This is the middle equilibrium of the three of them, or?
No, the bottom one. The middle one is kind of a numerical curiosity, but because it's unstable, a real planet wouldn't end up there. So you have to be pushed over to the left side of the unstable one, and then you run away to the
So there's a range of separations, I guess, where you have the three equilibria. You translate into the two stable ones.
That's right.
And so this is the beginning of this range, the end of this range, the middle.
This is basically where you no longer have so the Earth could have two stable climates. This is basically where you get to a point where there isn't a stable warm solution. There isn't a temperate solution.
So if you're below this curve, you're always close.
You're always close. That's right. Yeah. So how far out can you push the planet before it ends up just totally frozen, no matter what the starting conditions are?
And this is for what type of star?
For the sun. And so this is keeping fixed atmospheric composition. So the atmosphere is like the Earth, similar to greenhouse effect. What typically happens in models where people are actually looking at trying to calculate the outer boundary of the real habitable zone. Yes?
One more question. So the Earth is at 0, 1 on this plot. And so wouldn't this imply that the Earth is always frozen over? Are we really that close to?
At fixed atmospheric composition. So if we moved a little farther out, then there's a feedback called the carbonate silicate cycle, which tends to keep the amount of greenhouse gas in the atmosphere about right to have our temperature close to the freezing point of water, but a little bit on the warm side. If we kept the greenhouse effect exactly what it is, and we just moved the planet out even just a little bit, we would end up frozen over. But with 90-degree obliquity and eccentricity of 0.5, we found that there's a huge increase in the outer boundary of the where the snowball transition happens, relative to what you would have predicted by just scaling with the annually averages of stellar irradiation. So this is a planet with a semi-major axis of almost 2 AU, with Earth's atmospheric composition that still is habitable, and at least according to this simple model. And notice that if the semi-major axis is about 2 AU and the eccentricity is 0.5, then the apoastron separation is about 3 AU, and that's where it spends a lot of its orbit. Yes?
I really like this figure, and I can understand it better. What are the different curves?
I actually covered up the legend. So the different colored curves have to do with the rotation rate of the planet. So the rotation rate basically modifies the efficiency of the poleward redistribution of energy. Basically, because if a planet is, or to be equator worthy if it's high obliquity. Because when the planet's spinning faster, there's a stronger Coriolis force, which tends to inhibit latitudinal redistribution.
So the curves are the zero obliquity, and then there's two different sets of points for non-zero obliquity?
The various points have various meanings. I actually don't remember the meanings of all of them, but they have to do with the distribution of land and ocean, the obliquity, and so the obliquity is given by the color. So 90-degree obliquity is the kind of tan color. The point type, I don't remember the full legend of this figure. But the really key thing that I just want you to take from this is that there are combinations of obliquity and eccentricity that can result in dramatic changes relative to what you would have expected from a simple argument about how much energy the planet is getting from you. Yes?
Is the fixed composition, since you said the Earth is very sensitive to it, is that not a very good approximation?
Oh, it's a terrible approximation. But so what having non-fixed composition would do, I mean, this is basically just an experiment. This is looking to show where the actual outer boundary is. But what actually happens is that when a planet starts getting colder, it gets more, because of the carbon and silica, at least the Earth. It's maybe dangerous to generalize too much based on our geochemistry. But for the Earth, if it gets colder, it gets more CO2 in the atmosphere. And so the effect of not having fixed atmospheric composition would be that the distance where you go into the snowball transition would be even farther. Because as you go farther out, you start to get a CO2-rich atmosphere, the stronger greenhouse effect. So I think that this sort of result, if it turns out to be robust, could actually have important implications for the design and eventual target selection of a terrestrial planet finder mission that wants to take a spectrum of an Earth-like planet. Because it's considerably easier to get a spectrum of a planet that's at 3 AU from a star than to get a spectrum of a planet that's at 1 AU. So, another way that the planetary system architecture can affect the planet is by affecting the evolution of the eccentricity. Jupiter's eccentricity, which is pretty low, is about 0.05, is basically what I should back up and introduce that variation of the Earth's eccentricity has an important influence on the Earth's climate. About 100 years ago, there was a guy named Ludin Milankovitch who looked at the time history of glaciation and deglaciation events on Earth. And he saw that if you look at 3 astronomical sources of forcing on the planet, that the conjunction of the 3 of them are strongly correlated with the onset of glaciation and deglaciation events. So specifically, the variation of the Earth's obliquity, which is a very small effect. The Earth's obliquity varies by only a degree or two, between like 22.5 and 25 degrees. The variation of the Earth's orbital eccentricity, which is also very mild. The eccentricity varies between 0 and about 0.05 or so. And the precession of the spin axis. The precession goes through a full 2 pi, but precession doesn't do anything if you have non-zero eccentricity. I mean, sorry, if you have 0 eccentricity. And our eccentricity is always quite low. And yet, these 3 factors, and in particular the eccentricity cycle, these are called Milankovitch cycles, they're strongly correlated with very large changes in actual climate. Plunges us into an ice age and takes us out of an ice age. So it occurred to me that in exoplanetary systems, there could be very exaggerated versions of these Milankovitch cycles, because there's no reason why the terrestrial planet's eccentricity has to vary by such a small amount as ours does. Similarly, there's no reason why the obliquity has to vary by such a small amount. So if Jupiter's eccentricity were 0.4 instead of about a tenth of that, which it is, then it would drive much larger variations. Here we're looking at time on the horizontal axis and the Earth's eccentricity on the vertical. It would drive much larger variations in the Earth's orbital eccentricity, going instead of between 0 and 0.05 or so, it would go between 0 and 0.25. So the Earth would get to be as eccentric as Pluto and back down to 0. The mass of Jupiter would affect the time scale of these variations, but not the amplitude. So more mass of Jupiter would cause faster variations. The eccentricity of Jupiter affects both the amplitude and the time scale. So if Jupiter's eccentricity were somewhat less, then there would be lower amplitude and longer time scale variation. There's 0.4. You see basically what's over there. An inner planet can cause a very rapid oscillation. So here we're looking at if Jupiter were at 0.4 AU with an eccentricity of 0.2, it causes variations on just a several thousand-year time scale. And an extreme planetary system architecture, like an architecture that produces Kozai interactions, can produce very extreme variations in a terrestrial planet eccentricity, ranging between, here in this simulation, between less than 0.2 and more than 0.9. So this can cause huge changes in climate. And here I'm going to show you a movie that shows the influence of an extreme variation in eccentricity combined with a catastrophic event that plunges the planet into a snowball state. So we're going to be looking at the color here shows the temperature on the planet. Green is the temperature of the planet. And here is eccentricity of the planet. And compressing a Milankovitch eccentricity cycle that would have taken like 100,000 years or something down to 25 years just for visualization purposes. And between years 2 and 6, something catastrophic is going to happen that plunges the planet into a snowball state. Comet hits and kills off the dinosaurs or something. Now the eccentricity is going to start to grow. When it starts to grow, the planet is going to start to heat up. And it starts to transiently melt some of the ice during the local summer, but then the water refreezes. So I incorporated into the model the latent heat of freezing water. So it keeps on refreezing until there's positive net melting. Once there's positive net melting in a year, I say, as long as there's, even if you get just 1 centimeter's worth of net melting in a year, it'll just continue as long as the eccentricity is still high. So I just say that it's melted all the way through. Let's try that again. Missed the big climax. This is frozen over. The eccentricity is going to start climbing. It's heating up. Once we get to this pink color, that's telling you that it's at 273 Kelvin. There's some liquid water, but it's refreezing every winter. Now it's almost melting out. There it goes. So this is kind of a cute simulation. This sort of thing probably doesn't happen too often, but it makes the point that dynamical changes in the orbit could also help a planet to melt out of a snowball state on a much faster time scale than the roughly 10 billion years that it would take for geochemistry to release greenhouse gases. Yes?
How deep is the ocean here?
Well, so the ocean actually doesn't play a role here because it's covered with ice.
So you mentioned you put in the latent heat of water melting and freezing.
That's right.
And the amount of heat depends on how thick the water or the ice layer is.
That's right. So how long it would actually take for positive net melting to result in melting all the way through depends on how much net melting you get and on how thick the ice is. So if the ice is a kilometer thick and you get only 1 centimeter of net melting per year, it would take 100,000 years. I didn't include that in here. I just said as soon as you get positive net melting, I'm going to call it melted all the way through. Usually when you do get positive net melting, it's much more than a centimeter in this model. So on a time scale that would actually be close to 100,000 years, melting through a kilometer of ice would happen very fast.
And where does the latent heat enter?
Well, so energy goes into melting the ice instead of raising the temperature. Once the temperature gets up to 273 Kelvin. Below 273 Kelvin,
Yeah.
if you have an excess of heating over cooling, the temperature goes up. But once you hit 273 Kelvin, if there's an excess of heating over cooling, the temperature does not go up, it just ice melts.
But how long this phase takes will also depend on how much ice you have.
Sure, but whether you get positive net melting in a year is not how much ice you have. Just assuming you have a big amount of ice, you say over the course of a year, is there positive net melting or is it all refreezing? If I can have some that remains liquid at the end of the winter, then that's what I call positive net melting.
Oh,
Whether that happens or
okay.
not doesn't depend on
Okay,
how much
at that
ice.
point you declare liquid ocean.
And at that point I just
Okay.
bam, say it's melted all the way. So I'm not going to get to the entire talk, but I'm going to skip to talking about the what we can learn about the probability of abiogenesis from when abiogenesis happened on Earth. So to address this, I'm going to show you a little cartoon of the history of life on Earth. 4.5 billion years ago, the Earth formed. Around 4 billion years ago or so, would disagree maybe by 100 million years or so, but around 4 billion years ago, the Earth became habitable. Basically, the late heavy bombardment died off to the point, maybe it's 3.9 billion years, but about 4 billion years ago, the Earth became habitable and has been basically continuously habitable, perhaps with minor interruptions for about 4 billion years. Now, there's some evidence, and this is probably the shakiest point on here, there's some evidence that life began by about 200 million years after the Earth became formally habitable. I think most people would agree that by about 3 billion years ago there was life. A lot of people would agree that by 3.5 billion years ago there's some good evidence that there was life. I don't really want to wade into this, but just to say that the more optimistic reading of the evidence suggests that by about 3.8 billion years ago there was life on Earth, which means that, if true, life arose sometime in the first 200 million years after the Earth became habitable. And then down here, intelligence. So this basically shows up right on top of this, on this scale. So there's a standard argument in the origin of life community that goes like this. Life arose early. Life didn't have to arise early. So abiogenesis is probably a probable process. The analogy that I like to give is, so if you're sitting somewhere in Princeton and you want to know how often there's a deer outside your window. One way of trying to answer that question would be to go sit by the window and wait with a stopwatch and stop the stopwatch the first time that you see a deer pass by. If you don't have to wait very long, then that's going to tell you that it's probably a reasonable inference to say that there are usually deer outside. And if you do that here, you might have to wait, I don't know, decades or something to see a deer walking down the street. And it's probably a reasonable inference to say that there usually aren't deer right outside the window here. So this is the style of argument. It's a reasonable style of argument in some cases. So can we quantify how probable abiogenesis is? So I worked with Ed Turner on this, and we wrote a paper on this a few months ago. We made a common sense argument that even if life is rare in the universe, there's still a strong selection effect. It's not surprising that life arose early on the planet that we find ourselves on, especially if evolution requires perhaps billions of years to develop intelligence. And of course, in our case, evolution did take billions. We don't know if it needed billions of years, but it did take billions of years. So it's conceivable that abiogenesis is a very improbable process, but that on all the inhabited planets, or at least on all the 4 billion-year-old inhabited planets, all the intelligent creatures see early abiogenesis. It might be that there are plenty of inhabited planets where there's nothing intelligent and where life arose yesterday. But on the ones where there are intelligent creatures, maybe it takes so long to develop intelligence that they have to find early abiogenesis on their worlds. If we were to find life somewhere we didn't have to, that would count a lot more towards the conclusion that abiogenesis is a probable process. Okay, we can probably get through most of the rest of this. So, to sort of quantify this, we put together a simple model in a Bayesian framework to try to clarify the relative influence of data and of prior assumptions on the conclusion. One of the things that I ended up realizing was that some of the people who have made this sort of argument in the past have basically done a frequentist analysis, but they've drawn a Bayesian conclusion. The conclusion is that abiogenesis is probable, which really is a conclusion that you're not allowed to draw from a frequentist analysis. But if you try to do a Bayesian interpretation of what they were doing, you see that there was an implicit prior that guaranteed the result that they ended up finding. I'll try to show you what I mean by that. So we put together a very simple model, the simplest model we could think of that wasn't obviously the same. And that is that abiogenesis is a Poisson process. And there's a rate parameter, lambda, measured in abiogenesis events per unit time. The lambda could be like once per billion years or once per billion years or something. And so we calculate the likelihood function, the probability that we see the data that we see, namely that life rose sometime in the first 200 million years after the Earth became habitable, given a value of lambda. Then we want to use an appropriate uninformative prior. I say an uninformative prior because I'm not a biochemist. I don't have any prior idea of how probable abiogenesis is. I don't have any prior preference for any particular value of lambda. So I want to choose a prior that accurately captures my ignorance. Incidentally, I've spoken to, well, I'll get back to this at the end, but I have spoken to some biochemists about what they think a good prior would be, and it's not encouraging. So you might think a good prior would be, if I want a prior that captures my ignorance, I should take a uniform prior in lambda. And so here we're looking at probability density, lambda measured in per gigayear, and so here's the uniform prior. Here's what it looks like. Now notice this is 1,000 times per billion years, 500 times per billion years, 100 times per billion years. All of these would count as very probable abiogenesis. improbable abiogenesis is scrunched way up here along the vertical axis. So to kind of stretch things out a little bit, it's useful to look at the probability density of log lambda instead of lambda. So this is what the uniform and lambda prior looks like plotted against log lambda. So here's the prior, and folding in the likelihood function to get the posterior looks like this. So the fact that light showed up early on Earth does make improbable abiogenesis, small values of lambda. So this is once per trillion years, once per billion years, once per billion years. It makes improbable abiogenesis less probable, and probable abiogenesis more probable. But of course, there's nothing special about lambda being our fundamental parameter. I could have just as easily thought about 1 over lambda, the mean time until the emergence of light, as my fundamental parameter. If I had done that and taken a prior that's uniform in mean time, this ends up, from prior considerations, favoring improbable abiogenesis. Fold in the fold in the data, and I get a posterior that again increases the posterior probability density of large values of lambda and slightly decreases it for small values. But my argument is that the best uninformative prior, certainly among the ones that I'm showing you here, is a prior that's uniform in the log, as opposed to uniform in rate or uniform in mean time. So this one looks like this on the log scale. And if I look at the posterior from folding in the likelihood, it again makes improbable abiogenesis less probable, and the data makes probable abiogenesis more probable. I think it's more useful to look at the cumulative distribution function instead of the probability density. So again, we're looking at, here's the prior for uniform and rate, and there's the posterior. So the posterior didn't feel the influence of the data at all. It's right on top of the prior. Here's uniform and mean time. So this one says, on the basis of prior information, is already ruling out improbable abiogenesis. This one here is basically saying improbable abiogenesis is strongly favored on the basis of our prior knowledge. And the posterior basically doesn't feel the influence of the data at all. Both of these, I think, are unreasonable conclusions. I don't think that we have enough prior information to say one way or the other that, without looking at the data, that abiogenesis either has to be probable or that it has to be improbable. If we look at the log prior, and then the posterior, this posterior, or this prior, allows the posterior to actually feel the influence of the data. And you can see it makes improbable abiogenesis less probable, and probable abiogenesis more probable. But it does not rule out the possibility that lambda is very small, which would make life here on Earth fairly rare, even though Kepler is finding finding evidence that there are probably a lot of roughly Earth-like planets in our galaxy. Now, finally, if we were to find evidence of independent abiogenesis, perhaps on Mars, perhaps on an exoplanet, or perhaps what people sometimes call shadow life on Earth, which would be life on Earth that had a different abiogenesis event, which we might recognize if it were, say, not based on DNA and RNA, for example. We would know that it's a different kind of life. If we were to find that, that would count far more strongly towards the conclusion that abiogenesis is not very improbable. You can see this brown curve here, which is the posterior, taking into account the data for the Earth, and if, for example, we found life on Mars. Here, improbable abiogenesis is basically ruled out. If we had an example of life where there weren't this strong selection effect. Yes?
Would be different curves depending on whether the life we found is intelligent or not?
No. It would. That might affect if we wanted to do a similar analysis to say what's the probability of intelligence or less. But I think that's actually a more difficult problem to pose. But if you wanted to do the similar style thing, it would affect that. But it wouldn't. It wouldn't affect the conclusion of that. What would affect it is if we had some idea of when life grows on that planet, but it's not strong in such a way. So the early evidence of life on Earth certainly suggests that life might be common in the universe, but it's not inconsistent with life being arbitrarily different. And I'll stop there.
So do we have any questions?
The conclusions you flashed in the beginning at multiple points. Can you bring those up again?
Sure. So I didn't get number 4.
So one of your arguments about difficulty not being as big an effect on life around exoplanets might be based on the fact the ocean doesn't vary that much from the Earth or small large. How much is that a function of ocean coverage?
Strong function of that.
So if you took the ocean down to 10% of the surface area, would that change your conclusion for that?
Yes. Yes, it does. So also, if you take the ocean down to a small fraction, then the planet is less susceptible to a globally frozen state. Because it's probably not going to be able to have enough snow and ice cover to make the whole planet function.
Is that a combination of both the heat capacity of the ocean and the recirculation?
The heat capacity of the one.
Well, the ocean has quite a large heat capacity, so it can down that.
Right, well, that's the main thing. It has a long term. What is that?
Recirculation.
Oh, yeah, so on the Earth, the ocean does play a significant role in redistributing heat, but the biggest influence is the thermal inertia. Yeah.
So, with all of those last points, were you assuming habitability is the only requirement for abiogenesis?
Specifically, what I'm assuming is early Earth-like conditions, without specifying exactly what those are. But just, would we know, or would we think we might know, is how long it took life to show up on Earth given early Earth conditions. Okay, just suppose we had an ensemble of planets with the same conditions, whatever those were. What would be the mean time until life shows up? Or what's the rate at which life will show up? That's what we're going to characterize. So there might be, what you're kind of I think getting at is that different planets could have different boundaries. And Earth might be, so if you take that into consideration, there's also sort of a selection effect that suggests that we would probably tend to find ourselves on a planet that has a particularly high variability, as opposed to a planet that has a low variability. So if we're trying to generalize from the early emergence of life on Earth to how common life is in the galaxy, that's another thing that needs to be taken into account. Although it's certainly possible that we live on a planet with among planets that are 1AU from some star, you might have an anomalous low value, but that seems improbable.
So I would have thought, so you choose like the completely non-informative part, the part you really understand. And I would have thought, well, that if we know that like abiogenesis is a complicated process that takes some amount of time. So it's like you can't take that, you can't have an arbitrarily large valuable planet, say. And so if you take like the crudest way to do that, you could say there's an upper limit on what man.
Right, which you have to do actually in order to have a normalizable planet.
Right, but in most parameter inferences, you don't actually need to be able to normalize the planet. So
But in this case, you do, because the likelihood to in many cases, the likelihood function can take care of the normalization. Let's multiply the improper priors are okay in many cases. If the posterior can be normalizable, because the prior isn't. In this case, the likelihood just likes it better and better
Oh,
the higher the value
yeah.
generate. We need a cutoff to be able to normalize.
But the cut-offs, I was trying to think what, so if you just have a cut-off and you know that it has to be positive quantity, so you know it goes from 0 to is cut-off x.
It actually needs a lower cutoff. Yeah.
Right. I just thought the sort of mathematical apply, you might apply that as the uniform on 0 to x rather than.
But so what I was showing is that if you take uniform lambda from 0 to the maximum, that has the conclusion baked into it. The posterior does not fill the into zero. So that
Right,
suggests
but, I mean,
that it's not
that's,
higher.
but that's also a reasonable, that depending on how you apply that, it's also a reasonable conclusion. You know, the posterior doesn't have to. You need stronger.
No, it doesn't. But I don't see why a prior that's uniform in lambda is any more fundamental than a prior that's uniform in 1 over 2, which has exactly the opposite qualitative behavior.
I mean, yeah, I can accept that. I just thought if you use like a mathematical argument, you could then put all the constraints on which tell you essentially what is the positive prior. I mean, if you can't really define the constraints, then you've got to find what
I think the point is that it's a good idea to choose a prior that doesn't really have it doesn't have to be ambiguous. And that's what the long prior does, which the other two I was showing you now.
Gets your